Okay, welcome to another lecture about kinetics and reactor engineering. In this series of lectures, we're going to talk about transport effect on chemical reactions. Specifically, we will begin talking about diffusion and adsorption in porous media. Then we will talk about internal effectiveness factors and Thiele moduli. And then we will talk about non-isothermal effectiveness factors. And finally, talk about external transport in systems where you have multiple resistances. Okay, let's dive into our discussion of transport effects on chemical reactions. So in all the lectures before, we focused on molecular scale reaction mechanisms and their intrinsic rate laws, with no external transport effects. We formulated rate laws for homogeneous gas phase chemistry, for solution phase chemistry, and for surface reactions in catalytic processes. For homogeneous reaction chemistry, the intrinsic rate laws that we've already learned can be seamlessly integrated into larger scale kinetic models, the kinds of reactor design equations that you learned in undergraduate. For example, batch reactors, plug flow reactors, or stirred tank reactors with fluid components. For reactions that happen at fluid-solid interfaces, mostly catalysis, sometimes electrochemistry, we must also consider the morphology of the solid before we can formulate models at those larger scales. Does the reaction happen at specific sites on the surface, or is the entire surface reactive? Is the surface flat and uniformly accessible to the bulk fluid, or is most of the surface area buried in a network of pores? How is the network of pores connected? How large are the pores? And what diffusion regimes will prevail? How do the reaction and diffusion processes that are simultaneously occurring in the pores influence each other? We will learn to answer all of these questions, and along the way, we will construct pseudo-homogeneous models for reactions and transport processes in packed beds and porous media. We still describe the rate on a events per volume per time basis, even though the actual reactions may be happening at active sites at some dispersion, the number of sites per area, and we're in a catalyst with a amount of area per gram, and the catalyst has a density, mass per volume. If you take all of those factors and you multiply them all together and you do your accounting carefully, you realize that you can still describe things as events per volume per time and use much of the machinery that you learned as undergrads. Okay, let's take just a moment to think about what kinds of materials we're talking about. Diffusion may occur in the random pores of a granular packing. In some cases, you're going to be talking about fusion through a regular pore network in a zeolite or a MOF or an MCM41 material. And in some cases, we'll talk about materials that are soft, but that still have one impermeable part and one part that's with water or some other fluid where the molecules can diffuse through. Examples of those would be membranes or gels in applications from fuel cells to growth cultures for tissue engineering, for example. So this is not just applicable to hard stuff. You can use these kinds of ideas in all kinds of contexts. The basic idea here is that you have void spaces or pores, and you have obstructions, and the obstructions serve to make the diffusion paths longer and to restrict the cross-sectional area through which things can diffuse. An important consideration is whether the pore network is isotropic or anisotropic. This has to do with the structure and the interconnectivity of the pores and whether they have a difference in which direction you look at. The network that I drew at the beginning is an isotropic pore network, at least I tried to make an isotropic pore network, and it doesn't really matter which direction you consider transport through this network, they're all going to be about the same. On the right, you see a drawing of a different kind of material, for example, composite materials. If you put down impermeable flakes and they stack with a permeable material between them, then you end up with one direction of transport that's parallel to the flat surfaces of the flakes that would be easy and fast diffusion, and another direction of transport that has to circumnavigate each of those little flakes and go through the spaces between them that ends up being a very slow. Describing transport in these kinds of anisotropic networks is more difficult. When we're lucky, the grains of the material are randomly oriented after, and then we can kind of average over all those orientations and you get mysterious factors of 1/3 when you do the spherical trigonometry, but we probably won't get into that in this course. We're going to mostly work with isotropic pore networks for now. In an isotropic pore network, a very convenient model for diffusion is that you have an effective diffusivity that's given by the diffusivity in the fluid that fills the pores as though there was no other obstructions, multiplied by a void fraction, which is the superficial fraction of the volume that corresponds to pores. That's a hard thing to measure, and the devil's in the details. It, of course, depends on what kind of probe you use to measure the volume of the pore network. Assuming that difficulty can be overcome, then there's one more factor in here. In the denominator, you see a tortuosity, and that's the length of the paths through the pore network divided by the length of the straight line paths between the same points. This factor of tortuosity tends to be on the order of 1.5 to about 4. The void fraction for typical materials, about 0.3 to 0.6. Okay, well, how do we make use of this effective diffusivity that we just learned to calculate? We use it in a fixed law-like expression, as shown down here. So this is the flux in moles per meter squared per second, for example, and it's given by a negative sign multiplied by dA effective, this effective diffusivity, times the concentration gradient of species A. But what I want to emphasize here is that this is really where these models become pseudo-homogeneous, in the sense that this gradient is a complicated object, right? If you really try to think about what is the concentration gradient, do you follow the path that molecules take through the interstitial spaces and pores? No, not in this equation. It's really simple now. We just consider the gradient along straight line paths through the material, and we don't need to include tortuosity anymore in considering what that concentration gradient is. Similarly, when we calculate the concentration of species A, we just think about the concentration within the pores. We don't actually need to average over the region of the obstructions where there is no A concentration. It's already accounted for in here. And in fact, if you think about these two corrections that we've made, you kind of see why the expression for the effective diffusivity includes the epsilon and the tau factors in here. If you really tried to model diffusion through that pore network, then you would have to think about tortuosity, and it would reduce the transport rate. And if you tried to think about concentration accounting for all the regions where there's nothing, then you would get a factor of epsilon from doing that, right? So that's why the effective diffusivity looks the way it does. It has absorbed all those effects into an effective transport coefficient, and then we model everything as though it's diffusion in a homogeneous medium. Pay just a moment of attention to the units here. The diffusivity, this effective diffusivity, still has units of a regular diffusivity. It's meters squared per time, length squared per time. And the concentration has units of number per volume. The gradient operator here has units of inverse length. And so if you multiply all these together, you're going to get moles per meter squared per second, right? So there's 4 factors of length downstairs in the gradient of concentration, and 2 factors upstairs of length in the diffusivity factor, and that gives us this molar flux. Okay, well, what is this diffusivity A? Recall that we needed to know the diffusivity, species A, in the fluid that fills the pores. And that D sub A is going to depend on the pore size. It's going to depend on whether a liquid or gas fills the pores. It's going to depend on some obvious things like temperature and the properties of species A. All right, how big are these diffusivities that we've been talking about? Well, it depends on what medium fills the pores and how large the pores are, and of course some other properties of the fluid in the pores and the molecules themselves. If the pores are filled with a liquid solvent, then that solvent is going to have a viscosity, and the molecules that are diffusing in the pore and in the solvent are going to have a radius, which we'll call Ra. And of course, there's a temperature as well, and that affects the viscosity, but it also directly appears in the diffusivity. In this situation, we would use the Stokes-Einstein relation as a first approximation, at least, to compute the diffusivity of a small molecule in that solvent. And we're ignoring the pore itself. We'll come back to that a little bit later, because we assume the pore is much larger than the molecules of the solvent and the solute molecule of interest. Little pin malfunction here. In that case, the diffusivity is given by the Stokes-Einstein formula. So you see here the thermal energy in the numerator, 6 pi times the radius of the molecule, and that's the viscosity of the solvent. So it's a little bit unfortunate, we run out of Greek characters to use in these discussions. Mu in this discussion stands for viscosity. I would potentially change that to eta, which is another common symbol for viscosity, but soon we will be talking about effectiveness factors. No matter what we choose conventional symbols here, they're going to clash with some other conventional symbols. So how large is this number? It's about 10 to the minus 9 meters squared per second for small molecules in water at 300 degrees Kelvin. What if the pores are filled with a gas? Again, properties like temperature are going to matter. We're going to have to think about the collision diameter now. So this is going to involve the radius of the solute molecule Ra and also the radius of the gas molecule collision partners. We also need to know their masses, the solute and the molecules in the gas, and we need to know the pressure. So the pressure didn't appear before when we talked about Stokes-Einstein and diffusion in a liquid, but now the pressure is going to be quite important because it influences how close those gas molecules are to each other, which affects the mean free path for collisions. And that is really how this diffusivity is derived, is using the kinetic theory of gases with mean free paths and collision frequencies to estimate the size and frequency at which you take random steps in your random walk. Whole class could be taught on these kinds of things, but we're just doing a little refresher here. The expression for the diffusivity in that case has some numerical factors. We pressure in the basement, that's in the denominator. Sorry, you'll hear me say that now and then. And then there's a collision diameter squared down there as well. And then you get a t to the 3/2 dependence is a key hallmark of diffusion in the gas phase. And then this 1 over mass is the 1/2. How large is this? Well, for a small molecule in air at 1 atmosphere, typical size of this number would be on the order of 10 to the minus 5 meters squared per second. We're going to be mostly concerned with the typical sizes of these numbers. If you want a precise number, it's going to depend on the identity of that molecule, the identity of the gas molecules or the solvents, and how much they stick to each other, and a lot of details. Most of the time, for our purposes in this class, we only care about the order of magnitude of these numbers, and so it's useful to keep these two numbers in mind. When we use the kinetic theory of gases, we assume that the molecules are bouncing off of each other in computing the mean free path between these collisions. But if the pores are smaller than the mean free path between those collisions, then the molecules are mainly bouncing off walls of the pore. In that case, and you can then compare this mean free path expression to the diameter of the pore. Now, if the diameter of the pore is smaller than the mean free path, and you enter this Knudsen diffusion regime, size, the diffusivity is written down here. I haven't estimated the size of this for any reference case because it really depends on how big the pore walls are. You can see that this can take any value depending on what material you're talking about and how fine the pores are. We can think about pores that are even smaller. For example, in molecular sieve materials like zeolites and aluminum phosphates, these things have extremely small pores, and the size of the molecules are comparable to the pores themselves, so that the molecule is never really freely moving in the pore. It's always against the walls at some level. Sometimes these materials have a structure that might look something like this, a little drawing, for example, of a caricature of a phagocyte zeolite, with chambers connected by narrower sections along these pores in a three-dimensional network. So now a molecule might fit comfortably inside that chamber, but then if it wants to move from one chamber to the next, that's how it diffuses through the solid, then it has to distort and squeeze through one of these narrow pore openings. And that leads to an Arrhenius or transition state theory-like dependence on temperature, something completely different from the other cases that we've seen. So this is the expression for the diffusivity in that case. You'll recognize transition state theory at the core of this. The key feature here is that each time the event happens, that kT over h times the Boltzmann factor for the activation term, you're moving by a length L hop going from one chamber to another, and that gives rise to an L hop squared after considering the random walk. So again, there's a lot of details in this that I've glossed over. That diffusivity depends on the interconnectivity of the pore network, whether they're connected in 1, 2, or 3 dimensions will matter. Of course, that will also affect whether this is an isotropic diffusivity or an anisotropic diffusivity, and a whole lot of considerations beyond what I've talked about here. But the key hallmark in this case is this Arrhenius-like or a transition state theory-like temperature dependence. Okay, let's take a look at all of these together on one diagram. So if I plot the diffusivity, typical values, meters squared per second, versus the diameter of the pore, then what you see is that for the gases and the liquids in large pores, it doesn't matter how big the pore is. You reach a plateau value that corresponds to the diffusivity in that medium. So for the gases, you have long steps in your random walk. Long mean free paths here lead to a large diffusion constant of about 10 to the minus 5 meters squared per second. And of course, that value depends on what pressure we look at. For a liquid with the viscosity of water, the diffusivity that you get is about 10 to the minus 9. If you let the pore diameter become smaller and smaller for a gas, a mean free path eventually becomes the diameter of the pore. And that enters then this Knudsen regime on a log-log scale. You see a slope of 1 here, that the diffusivity is scaling with the pore diameter and getting smaller and smaller as the pore diameter shrinks. It's no coincidence that the Knudsen regime ends down here at a round place where it intersects value for liquid water. When your pore gets so small that your molecule is constantly bumping into something, it's diffusing in similar fashion to the way that it would in a liquid. And if you try to make the pore any smaller than that, then you start to have constriction, thermally activated process to go anywhere, and that's where you enter this configurational regime. And the diffusivities in the configurational regime can get extremely small. So, we'll always be conscious when we have molecules in this configurational regime. That's where we have to be really careful if we're working with a zeolite or something like that to think about particle size. So if we make the particles too big, the entire interior of the particle will be inaccessible in a reasonable timescale. For more on these topics, check out the textbook by Kussler or the textbook by Hirschfelder, Curtis, and Berg.